Hello, thank you for coming. My name is Nicholas Malaya. I'm over at the University of Texas, just a few blocks from here. I'd like to talk to you about MASA, which is a tool, a software library we've developed. But in particular, even more broadly, I'd like to talk to you about verification of scientific software. I think it's something that's very underappreciated in the scientific community and more broadly. So just to give you an overview, I'll give you a motivation for verification. I'll define what I mean by verification, in particular software verification, and even more specifically, really, numerical verification of any predictive software. And then I'll introduce the method of manufactured solutions. This is something we use very commonly, and I'm not sure how much it's gone through the community. And I'll try and prompt both some of the ways we create a manufactured solution, and then more broadly give you a sense of how this is difficult, it's non-trivial, and therefore why we should have a central repository for this sort of thing, and then introduce MASA, which we believe is a solution for it. And this talk is online. It's at Manufactured Solutions or Manufactured Solutions on GitHub, where the library exists as well. So just as a fun verification failure, I don't know how many of you have heard of the London whale. This happened, I think, in 2012. It was a JP Morgan synthetic credit portfolio, and this comes from the report that the JP Morgan actually came out with. It said that it was a model that was developed by a quantitative expert, mathematician, and model developer. I think that could apply, those words could apply to some people here, although hopefully not in the result. And then it's, again, from the report, the model operated through a series of Excel spreadsheets. They had to be completed manually, a process of copying and pasting data from one spreadsheet to another, so obviously this is a bad start. It resulted then in a loss of $6 billion and another $600 million in fines. So this is a catastrophic verification failure in that the model failed in a serious way, and it actually was underappreciating the model, the volatility of these underlying instruments by a factor of 2. And it was quite simple. The result, the error in it, the bug, was that the spreadsheet divided by the sum instead of an average. So this is kind of a classic example of a verification failure in that you had a bug in your software, it makes a faulty prediction, and bad things occur. And this can apply to more than just finance, obviously. As scientists, we're making predictions in a broad range of fields. You can imagine failures of verification causing bad things to happen in predictions such as global warming, designing the lift or the drag on a Boeing 787, earthquakes, hurricanes, storm surges. On the bottom here, you'll see this is the Orion reentry vehicle. This is something that we do at the Pecos Center at Texas. This is related to my research. We are making predictions on the heat ablation rate on the heat shield for this reentry vehicle. So you can imagine that a critical verification failure here could result in actually the death of astronauts. So it's something that you don't have much room for. So just to define what precisely I mean by verification, if you look at the top here, you have a picture of our friend Usain Bolt running, sprinting. This is reality, right? This is a real person running. As scientists, as mathematicians, when we create a mathematical model, that might be Newton's second law, it might be any sort of model, that's not necessarily going to correspond to our friend Usain, right? It may not predict it perfectly. That jump there is what we'll call validation. The question of how accurately your mathematical model represents reality is a validation. That's not what we're dealing with. We're dealing with the second bit here to the third. This is where you have a mathematical model. You can write it down on a chalkboard, but now you need to instantiate it somehow in Python. You have to discretize the equation in some form. And obviously you're making assumptions. They're digital computers. You're not able to perfectly represent what you wrote on the chalkboard, and you're not able to perfectly solve it. In this case, you might make a second order finite difference, and you see there's a second order term here. This big O notation suggests that there's a residual, that your finite difference representation does not perfectly represent the operator, but it does asymptotically as you shrink your mesh, as h, the size of your discretization, shrinks. So I think this is a good definition of verification of scientific software. It ensures that the outputs of a computation accurately reflect the solution of the mathematical models. And this isn't unique to even scientific software, obviously, unit testing, regression testing, but what I'm going to focus on subsequently is really the concept of discretization of, in general, differential equations, but you might even think of algebraic equations, but mathematical equations. So I think the 2 points here on the bottom you'll see that are very important are the errors from the numerical discretization sufficiently small? How do you know that? How can you characterize that? And then is the convergence rate consistent with the numerical scheme? That's that big O term I showed you previously. And obviously the thing that would be great here is that you could characterize both of those questions. You could answer both of those questions if you had an exact solution. So if you had a PD, you knew what the solution was, you could look at your computer code's numbers and you could take some sort of appropriate norm and you could compare that to the exact solution, and you could look at how it converges as you shrink your mesh size, as you change your time step, etc. But obviously the reason we're doing computation to begin with is that we do not actually possess exact solutions, or we wouldn't be doing computation. So we need something that acts as a surrogate in this context, and this is what we call the method of manufactured solutions. So we might not have the solution, or even the solutions in the cases you have it, they might not fully capture some of the dynamics of your equations. So all we're going to do is we're going to try and emulate exact solutions by creating something completely arbitrarily. It's a mathematical trick. So as a simple example, here's Laplace's equation. Right, hopefully everyone is comfortable with their multivariate calculus, but so you have a two-dimensional operator here. And let's just completely arbitrarily say that phi here is a solution to Laplace's equation. So phi down there, you can see the color's not coming through too well, but Ly and Lx here are just constant parameters, and then we have these quadratic forms that would satisfy the equation. But anyone who actually sits down, pen and paper, and writes it out, you'll see that it doesn't actually satisfy the equation. The right-hand side, the residual, is non-zero. So there's something left over. So lo and behold, shock of all shocks, the thing I conjured up out of the air does not actually solve the equation. It's never going to, because these are complicated equations, and again, if I had an exact solution, I'd be done. But what we can do here is, with this residual, now having calculated it, we can use this as a forcing term, as what we'll call the source term. We add this to the right-hand side of the equation, and now we do satisfy the equation for this particular system. It's not necessarily physically relevant, but it does capture and it does satisfy the mathematical operator, and that's really the whole trick here. So we can satisfy and we can actually verify the mathematical operator that you're interested in by adding the source term, and then we know what the exact solution will be. So one might, in this case, for a second order central difference, like I showed, for the 2D Laplace's equation, using exactly the solution I presented previously, we'll add this f to the right-hand side. We can put this together. We can solve it numerically. And what are you going to get? Well, what you'll do is you'll see that on this plot we have the L2 error, that's just the error norm, as a function of the grid spacing. And so as you shrink your mesh, you see that it converges, it drops, and the rate of the error there, the slope of it, is, in this case, I guess, found to be negative 1.945. So we expect it to be roughly 2, right? So this is not quite 2. That's going to be typical. That's because it's not asymptotic. You haven't shrunk your mesh enough. You need to keep shrinking it, and it'll approach 2 asymptotically. So this is an example of a case in which it works. Let's look at it. It's not going to be subtle when it fails. So in this case, on the right here, you can see a plot where that red line does not continue to converge at the second order rate. So what we've done is we've created a manufactured solution for, in this case, a somewhat non-trivial mathematical operator. It's the Navier-Stokes with Favre averaging. And you see the red line does not continue to reach the convergence rate we'd expect. And that's because of the presence of a bug. And I want you to look at, if you can see, and the axes are a little small here, I apologize for that, but notice that you're looking at 1 part in 1,000 on the left side here. So this is detecting a very subtle bug that you're not going to detect with your eyes. You're not going to just look at this solution and say, oh, there's something wrong here. But these sort of bugs, which we'll discuss in a moment, it was actually a very serious bug, could blow up in other regimes. Just because you're testing in one doesn't mean that this isn't going to be catastrophic in another. And in particular, when we looked at what was causing this, we found the bug. It's not something that's completely obvious. It's on the left side there. You can see the correct derivative at the top, and then what was in the code on the bottom. And so I don't think anyone's scanning over this without really focusing on this section, without seeing that there's a verification failure, would know that you've been missing the parentheses there. But that is a serious bug and could have blown up in other regimes. So that's the sort of thing that this is very powerful for testing, and I would propose it's an extremely powerful test. You can really push this down into machine precision and ensure that your operators are behaving like you expect. Often, you're not going to be doing this by pen and paper, though. You're not going to do like the Laplace example I showed you, because your operators are complicated and the manufactured solutions you're looking at are going to be non-trivial. So this is a very typical one in the community. It's essentially the sum of sines and cosines, and it's nice because you can get it to satisfy essentially any boundary conditions you're interested in. So if you took this operator, or this manufactured solution, and you plugged it into a typical industry operator, say the Navier-Stokes three-dimension energy equation, what are you going to get? Well, let's do it using symbolic manipulation. You could use SciPy, Maple, Mathematica, anything like that. And here it is. So I suspect not many of you are going to want to do this by hand. And in fact, if you look very carefully at the bottom right there, you'll see there's a little plus, because I cheated, and there's actually a few more pages. So clearly, you're not going to do this by hand, but you can, using symbolic manipulation, create these sort of terms, and then very easily instantiate it as C code, as anything you want, that you can then use as your right-hand side. So this has generated this right-hand side for you. That's now just a function call that you can evaluate to force on your operator and perform the verification. But at this point, I hope you can appreciate that this is a little non-trivial, right? You've created this source term offline. You now have it so you can perform a verification. But this is a valuable thing. It's typically not published, these sort of source terms. They're not, even if it is published, where are you going to get this right-hand side? Are they going to provide C files or a Python file for you? Often they don't. So there's a utility that we can reuse this in the community by actually putting these somewhere that it can be publicly accessed. And so that's where we enter into to MASA. This is the library that we generated because we were generating a lot of these manufactured solutions, and we were working with some of our collaborators at the national labs and such. And we found that in some cases we actually did generate the same thing that they did, and vice versa. So we're trying to create a community-based platform where we can all instantiate these, we can contribute. It's open source, and we can access this publicly, and then ideally publish this and become, improve verification across the community. So obviously we need it to be extremely accurate to the generated MMS. I'll talk about that very briefly. So people need to trust it. If I give you a manufactured solution, you need to actually believe that this is correct, even discreetly. It needs to be portable. It's going to be used across a wide variety of platforms. Traceability in terms of documentation. What actual operators are you solving? If it solves the wrong operator and it doesn't tell you that, obviously it's useless to you. And then extensibility. We really need this to be a community tool. Unlike most HPC or scientific computing, it's actually, performance isn't a huge issue here. But I think it's not going to be so slow that it kills you. So our error targets are to push it towards machine epsilon. We tend to force the regression tests for this to be less than 1 part in 10 to the negative 15. That's pretty strict if you push it. So this is for, of course, double precision. To do that, MASA, the library, actually enforces O0, and in fact, it typically for compilers, this is all for C, the underlying C code, has even stricter flags that it'll impart on it to enforce it, because Intel in particular is making a lot of speed tricks even at O0 levels. We have a series of regression tests. You have to believe that this library is actually working, so we have more than 65 tests now, actually, which run over all the different features, all the different manufactured solutions, tests that whatever you've built on your platform still works. So here's a little snapshot of the library. It's all hosted on GitHub, as I mentioned, so it's using Git for version control. We have an automated regression. Obviously, there's also the Travis CL, but we're using BuildBot on our side, which is a automated regression testing. And then you notice that we have 15,000 lines of code. It's not too big of a library, but we actually have 13,000 lines of testing. So we're really trying to pound this down so that you can believe this, so that you'll then believe it when it says your code either works or doesn't. And that comes out to using, I guess, gcov to be about 98% line coverage. So that's pretty good. It is obviously, this is SciPy. I wouldn't be here if it didn't have Python interfaces. We're finding increasingly that there are a lot of scientific users using Python, and so it has Python interfaces as well, but the underlying kernel is C, C++. So just a quick example of the API. It's really straightforward, but after you've installed, as long as you have your Python path, you can import a MASA module. You then would call something like MASA init, where here you give it a string defining one of the manufactured solutions that you'll need. And then you'll evaluate this guy at the source terms at some point in space-time, and likewise with the manufactured solutions. And calling those are just function evaluations at those points in space. So you'll be doing this over every point in space. This is kind of the general arc of how you interface with MASA. You initialize, you do your model solve, in which you add to the right-hand side, as I showed you before, the source terms. You iterate that over your temporal loop. And then offline, you'll change the number of mesh points, and you'll create some sort of convergence plot like I showed you previously. And that should give you convergence rates and really show you if this is working like you expect. These are the present solutions we have in it. Obviously, this looks relatively particular to our particular domain, which is fluid flows. But it's much broader than that. MASA is in principle capable of essentially any mathematical operator, so Einstein field equation, Schrodinger equation, Black-Scholes. It's very broad in that sense. But obviously, we're only going to develop for what we're interested in. So we've developed a component of MASA that enables you to import solutions. This we accomplish with automatic differentiation. There's several great libraries out there. Theano is one of the Python available ones. Of course, when there's several great libraries out there, you do the natural thing, which is to develop your own library, which is what we did. But we did that in part because we wanted to keep the number of requirements down. So essentially, all you need to build MASA are C compilers. And just to show you, this is kind of a simple example, but the automatic differentiation is very powerful. It generates the source terms for you. So I just want to show you. You look at the top there. That is actually the manufactured solutions I showed you previously. So it's just a sum of sine and cosines. You instantiate that. And then for, say, the divergence operator, the C code is actually very straightforward. So you see raw value divergence of rho u. And that will generate the entire continuity source term for you, using automatic differentiation. So I think it's a very powerful way you can instantiate operators yourself. And ideally, we'd like people to either develop these themselves, C, C++, Fortran, or use the automatic differentiation and then propagate it back into the community, back to the library where we can all use it. Obviously, there needs to be a willingness to share. Some of our lab partners have been a little queasy about using the library because you can imagine that some of the manufactured solutions they're generating are not things that they would like to share. But aside from that, I think we have community users. We're getting people to propagate solutions back, and we're interested in broadly using it as a tool for the community. So this is just a snapshot of where we are right now. As I said, it's on GitHub. Welcome contributions. Please check it out. And then just something to keep in mind for the academics in the crowd. Increasingly, as this has become more of a community accepted standard, there have been publications where you can actually publish some of these manufactured solutions. It'll propagate. There are journals that'll accept it. It's not particularly high impact, but it's another way in which you can actually get credit for the work you're doing, ensuring that your code is accurate. So that's where I'll end. Just with some summary. I'm happy to take any questions, and thank you.